Let's take a look at D. Let's notice in D, let's try cutting along the x-axis. If you cut it along the x-axis, nope, you don't get the same picture above and below. However, if you do cut it along the y-axis, you do get the same picture on the left and the right. So this will have y-axis symmetry. Now what happens if you turn this 180 degrees is you will not get the same picture. So the only thing that we have here is the y-axis symmetry, and that's it. Now in the next group of examples, we want to test for symmetry again, but these we don't have pictures. We just need to work with the equations. There's no pretty way of doing this. We talked about this a minute ago, is you've just got to do these out by hand. So you still have to do them one at a time. Let's start out with x-axis symmetry. If we want to test for x-axis symmetry, it means wherever there's a y, we're going to plug in, and wherever there's a y, we're going to plug in a negative y, and the question is, will the function be the same? So we'll start out with the original function, which is y equals 2x to the fourth minus 3. And what this is telling you for x-axis symmetry is you got to replace any y's with a negative y. So we'll replace that y with a negative y. Everything else will stay the same. The question is this the same as the original? Well, there's no way to do this unless I leave y by itself like it is in the original. So I need to get rid of the negative sign by dividing by a negative 1 on everything on both sides, which gives me that y equals, well, I'm dividing everything through by negative 1, so that'll turn this 2 into a negative 2 x to the fourth. But I also have to divide the negative 3 by the negative 1, which will turn this into a positive 3. Now I need to compare this to the original. Are these the same? And the answer is no. So does it have x-axis symmetry? No, not at all. Problem with this problem is I am not done. I still need to test y-axis symmetry and origin symmetry, so I need to keep going. So now let's test y-axis symmetry. How we're going to test y-axis symmetry is by plugging in negative x wherever there's an x. So we've got y equals 2x to the fourth minus 3. And plugging in, let's see, a negative x wherever there's an x. So we've got a negative x that's going to go in here for our x. So that'll leave us with y equals 2. The negative x will get plugged in for the x, which is raised to the fourth power and has a minus 3. Now notice we have a negative raised to the fourth power. What happens when you multiply a negative times itself 4 times? It becomes a positive. So the negative will disappear and become a positive x to the fourth. And you'll still have your minus 3. Now what we want to notice here is is it the same? Absolutely. So the question is, what does that mean? Well, the function stayed the same when I plugged in a negative x wherever there was an x because I was testing for y-axis symmetry. So it means that we do have y-axis symmetry. However, again, you are not done. You still need to test for origin symmetry. Remember, an origin symmetry is a combination of the two. So we actually need to do 2 things. We need to plug in a negative y for y and a negative x wherever there's an x. So the original equation was y equals 2x to the fourth minus 3. We'd be wanting to plug in a negative y wherever there's a y. So the y would get replaced with a negative y. And we'd also want to replace the x's with a negative x. So we'd replace our x that's coming next with a negative x, which is raised to the fourth power. Next, we'd want to do any math we can do. Well, we'd start off by saying, well, anything that's negative that's raised to a fourth or even exponent is going to turn into a positive. So that'll be a positive x to the fourth. However, I need the y by itself, so I'd still have to deal with that negative out in front by dividing everything on both sides by a -1. What that would do is then turn this into y equals, let's see, the 2, because we're dividing by a -1, would become a -2, x to the fourth, and then we're also dividing the -3 by a -1, which would become a +3. The question is, now that the y is by itself, is this the same as what we started out with? And the answer is no, not at all. So does it have origin symmetry? Absolutely not. So this first problem, the only thing that we can say based on what we did is that it has y-axis symmetry only. That was the only one that worked. Okay, the problem is that's one of the problems. We still have 2 more to go. So this can be a pretty good sized pain to deal with. So let's try another one. In problem B, let's start out the same way that we did in problem A by looking for x-axis symmetry. Remember, if we're testing x-axis symmetry, we actually do the reverse. We plug in a -y wherever there's a y. So our original function was y squared minus x squared equals -6. So we'll plug in, let's see, a -y wherever there's a y. Well, notice plugging in the -y for the y, remember that's going to get squared according to the formula. So we get equals -6. Notice what happens. What happens when you square a negative? It becomes a positive. So squaring a negative becomes a positive. So that'll just become a positive y squared. We have the minus x squared and the equals -6. Nothing else has changed. So let's compare it to the original. Are they the same? Well, they're both a y squared minus x squared equals -6, so yes, they're the same. What does that mean? It means that yes, indeed, there is x-axis symmetry here. Still not done, though. Just because one worked doesn't mean that there aren't more that worked. I need to now move on to the y-axis symmetry. Which means, remember, for y-axis symmetry, we're going to do the reverse. We're going to plug in a -x for all my x's. So our original equation was y squared minus x squared equals -6. So this means on this one, I'm going to plug in a -x where all the x's are. So I'm going to replace my x with a -x. So that will give me, let's see, y squared minus our x will get replaced with a -x, which is, again, squared. Everything else will stay the same. So the question is, what happens when you square a -x? Well, it's an even exponent. What happens when you square or do an even exponent to a negative number is it will become positive. So that'll just become a positive x squared. The -6 will stay the same. So now let's compare it to the original. And what do we notice? We have a y squared minus x squared equals -6. Are they the same? Absolutely yes. So, does it have y-axis symmetry? Yes. I am still not done, though, because I still need to see if I have origin symmetry. Which means I'm plugging in, let's see, a -x for wherever there's an x, and I'm also plugging in a negative y wherever there's a y. So I'm doing both of these things. I'm plugging in negative y's for y and negative x's for x's, and I'm hoping that everything will stay the same. So our original equation was y squared minus x squared equals negative 6. And I'm going to replace any y's with a negative y, which notice the y's are squared, minus, I'm also going to replace my x's with a negative x, which is also squared. So the question is, what's going to happen here? Well, as a reminder, what happens when you square or do an even exponent to a negative is it becomes a positive. So this will become a positive y squared. But for the same reason, that means the negative x squared is also going to become a positive x squared. We still had the minus in between, equals a negative 6. The question is, how does that compare to the original, and is it the same? And the answer is yes, it is indeed the same. So what does that mean about origin symmetry? It also has that, which means at the end of the day is that this problem has all three types of symmetry. So it has x-axis symmetry, y-axis symmetry, and it has origin symmetry. All three. Now let's